Next, we have Bruno Mattos from Utah State University to talk to us about thermal and radiation design considerations for CubeSats in low lunar orbit.
Okay. Hello, everyone. My name is Bruno Mattos. I'm a PhD student here at Utah State University. On behalf of my co-authors from USU and ITA Brazil, today we're going to be talking about the thermal radiation environment in the moon. We're going to focus our analysis on a low lunar orbit in a perspective of operating there with CubeSats. All right. So, as you probably know, we are living in a very exciting time for the CubeSat community. We are going back to the moon, and at this time we are bringing a lot of CubeSats with us. Artemis 1 launched 10 CubeSats. We can see there the Orion stage adapter. And unfortunately, half of them had a lot of problems right after the deployment, which show us that going to the moon with CubeSats can be hard even in the beginning of the mission. We're going to be focused here what happened when you arrive there, especially in low lunar orbit environments. We believe that flying low and especially flying over the poles has a very scientific appeal for us. So we're going to try to study that environment on that perspective. The analysis is going to cover basic stuff from the environment, and we're going to try to derive some considerations that we might apply for many missions in the future. So, jumping here on the thermal part, this picture is very nice to see the difference between Earth, the IR environment for Earth and the moon. Fun fact here, moon on this perspective, our moon looks very similar to Mercury on the temperature gradient across the surface. Moon doesn't have any atmosphere to help spread that heat across the surface, so we have that big gradient on temperature. When we are analyzing Earth, we usually consider an average, and average is fine. To 55 Kelvin, it's okay, because we can see there's not a lot of big change. Even the poles are not that different from the equator. But the moon, we're gonna have to be more cautious about how we're gonna approach the thermal design of our spacecraft. So first of all, we're gonna be talking here a lot of beta angles for high inclined orbit. That's something really important. So when I say 0-degree beta angle, just for everyone to understand, that means that we're going to be flying over the subsolar region where we face a lot of IR radiation. The orbit changes over time, so that high inclined orbit gonna be over the terminator line, so a high beta angle in that condition. The plot on the right part here shows how that beta angle changes over time. So during 1 year of mission, we go from 0 to the 90 degrees. Many times, actually 3 months lasts from 0 to 90 degrees. We can see that when we are flying with a low beta angle, we have a high IR condition. And when we are approached to 90 degrees beta angle with a 90 degrees inclination orbit, we start to have low IR condition and more intense and continuous solar flux in one phase. Approximately 40 days there, seeing the sun constantly, being exposed by sun, and we're gonna see that also means that we're gonna be more exposed to radiation coming from the sun. So to calculate the IR flux, we usually start with modeling that surface temperature, and then we apply an integration. We discretize the moon in many patches. We consider the view factors of those patches with each face of our satellite, considering a fixed point and condition, and then we come up with the IR flux on each face. So let's take a look on how is the profile of the IR flux on each face. Here we start with 90 degrees beta angle. That's would say the cold case. Very low flux. The problem with IR flux comes here. When we are flying over the subsolar region, especially the nadir phase, gonna face a lot of IR flux. If we compare to what we get here from in low Earth orbit, You can see the dash line there. That's usually how much flux we get in the nadir phase. So around 50 minutes, that's for a 100 kilometers altitude orbit, we're gonna be facing much more IR on the nadir phase. So we're gonna have to be more cautious how we design that nadir phase, especially trying to insulate from this IR flux and try to mitigate the swing on temperature on that phase, and of course in everything that's attached to that phase. We can also analyze solar. Solar means direct solar flux and also reflected by the surface. Fortunately, the moon has a very low albedo. Here we are using 0.07. In Earth, we usually use 0.3. So we can see that when we are in the 90 degrees beta angle, one face on the left chart, we can see the Y plus face. That face is facing the sun constantly through the orbit, and the other faces are pretty much in the shadow. The other plot is a very common one where the sun goes from the RAM phase, anti-nadir, and anti-RAM phase. Okay, so we can calculate average of those profiles. So let's compare orbital average from Moon and Earth and see what's the variation. Now let's start with that case that we are flying over the subsolar region. So we can see by the solar flux, we get less solar flux when we are flying the moon, but the IR flux on the right side, we can see that we start to receive, on average, much more IR on the moon. That's gonna make our life much harder to dissipate heat when we are on this condition. For beta 90 degrees, we are flying over the terminator line. On this case, the IR flux drops significantly. We can see that in comparison to Earth, that condition is much better on the moon for the beta 90 degrees. Solar flux does change a little bit. You have to consider that on the moon we have less seasoning effects because of the angle of the ecliptic plane is much lower than here. So we can apply those orbital average and apply for one case. In this case, let's do a 6U case on where we are flying on that configuration. The 6 phase facing the RAM direction and the 2U phase facing the nadir. Here we are comparing what is the instant power, right? Is the flux times area. For Earth, we can see that when we sum the solar flux with the IR for the hot and cold and see the difference, we see that the environment just changed about 15%. When we compare when we are operating on the moon, for that flight configuration, that change can reach up to 68%. So the environment, in terms of total environmental loads, really changed significantly. If we compare the hot on the Earth and hot on the moon, we can see that the IR on Earth 16 against 29 means that even though the total environmental thermal loads are similar, 69 to 74, the distribution between solar and IR change. And when we have more IR, that means that we're gonna have some difficulty to dissipate our heat. Okay, so one strategy to try to fly a high power CubeSat is usually to have a high IR emissivity in our face. We wanna reject the most heat as possible. And that's the same rule for the moon. One thing that we need to make sure is we can survive the eclipses. We call solar eclipses there, and they're much longer than whatever we have here on a low Earth orbit. So on this case, on the next decade, we can see that we're gonna have 6 long solar eclipses there. If we take the 2029, which is the longest one, it's about 4 hours duration. And we need to make sure that our satellite has enough battery to survive and keep our satellite warm. Keep in mind that when we have the Earth blocking the sun, the moon will get cold really fast. So that spread on temperature, that 390 Kelvin, gonna disappear in the first half an hour. So we need to make sure that our satellite has enough thermal mass and enough battery, and the heaters are located in the right place to keep our satellite warm. So we can see that a 6U from 12U is about 60% difference on how much battery you need. So main takeaways here for the thermal part, you need to be cautious about the nadir phase. The nadir phase is going to swing a lot if the IR emissivity on that phase is high. So we probably want to insulate that phase and make sure that we have a low IR emissivity. That also means that we have less area to reject power. So we need to balance that correctly. The side phase with a high IR emissivity, we will also experience some swing, and we need to make sure those temperature changes are inside our envelope. In that condition with the beta 90 degrees, of course, we have that phase seeing the sun constantly, so we need to be cautious and maybe use a low alpha, low solar absorptivity on that phase. And of course, components installed in the nadir phase, we need to do a more detailed analysis and make sure that we are in the acceptable range of temperature. So let's move on to the radiation environment, because the thermal is not the full story. For the radiation, we can see that when we are operating on the Earth, we have the magnetosphere to protect us, even though that we have some consequences like the South Atlantic anomaly that also impose some risk for our operation. But when we are in the moon, we have no magnetosphere to protect us, so we're gonna have the full solar wind power hitting us there. We also have GCRs coming from all directions in from outside of a solar system. And of course, we're gonna see that solar particle events like solar flares or CMEs can also hit us very badly and can cause real damage. So we need to be cautious that we are in the solar cycle 25. Here I show where we are expecting to have the next 4 Artemis mission. We can see that the predicted values for the sun activity is much lower than we are seeing when we are measuring. Those are sunspots. It's nice to also realize that GCRs is modulated by the sun activity. When we are in the maximum solar activity, we have less GCRs, about 15% difference. However, we're gonna fly probably on Artemis 2 and 3 in the high peak, and more solar particle events are likely to happen. So we can analyze the total ionization dose and try to compare. Here we run some SPANVIS simulation, and I plot there the 2 usually thresholds that we start to thinking about degradation in our parts for commercial and semi-hard. And we can see that for a 5 millimeters aluminum thickness, we almost achieved the 2K rad dose, only considering regular solar wind. And that doesn't take into account the dosage that we also received during the travel to the moon. What is more concern is, of course, solar particle events. They are very unpredictable and very hard to see what's going to be the likelihood to receive such powerful energetic particles. And we can see that the moon is much worse than operating in a sun synchronous or in the ISS orbit. Okay, so we need to start to thinking about how to make our CubeSats more resilient. And of course, we can try to, well, first we can try to go bigger, right? With a 12U, we have more room for shielding, for putting more, putting redundancy. And talking about shielding, one thing that we need to be aware is maybe sometimes aluminum, increasing the aluminum thickness is not the answer for shielding our spacecraft. We need to consider also the use or more effective materials. Here I'm showing the Z-grade materials used on the Shields 1 CubeSat launched in 2018. And also hydrogen-rich materials that helps to slow down those high particles that are coming from GCRs and strong SPEs, like polyethylene, plastic, and Kevlar. Thinking about applying those type of materials, trying to encase some sensitive chips like memory or microprocessor can be an answer to increase our resilience and increase our survivability there. Also, when we are operating with COTS components, we can also try to do cobalt-16 and try to see and select what COT element is more resilient than the other, and select the ones that are more hard for against radiation. So that's it. Thank you so much, and see you on the moon. Yeah.
We have time for one quick question.
Hi, fantastic thermal analysis you've done there. One question I have is, have you considered the use of novel smart materials like variable emissivity materials or variable absorptivity materials to address the challenges?
Perfect. Yeah, actually, I forgot to mention that. USU has developed a very nice system for dissipating more heat. It's called ATA, has a deployable radiator, so we can use more advanced techniques if the requirements of the mission we need to apply that for fulfilling the requirements. And also changing the emissivity especially for the side faces, I think is something that we should consider using those more advanced materials. Yeah.
Awesome, thank you. And let's talk afterwards.
For sure.
And yeah, maybe you can talk with Bruno afterwards.
Thanks.
Thank you.
Thank you.
Thank you.